This video we're going to talk about what linear equations are. Right? Last video we talked about the Cartesian coordinate system. And it's not just for plotting some dots in random locations. It's more or less for graphing actual, what we're going to call functions. And the simplest of all functions we can talk about are what are known as linear functions, or more generally, a linear equation. Well, a linear equation takes on the form. Now this capital A just represents any number, any number you could possibly think of, times the variable x, plus another number, any number you could possibly think of, times a variable y equals a third number. Just, you got to make sure the numbers you pick for A and B, they're not both 0. One could be 0 and the other cannot be a 0. That's not a problem, but they can't both be 0 at the same time. So, to give you an example of what a linear equation might look like, it might be 3x minus 2y equals 7. So you can see in an equation like this is a linear equation. Notice the x and the y. The capital A would be the 3, and the capital B would be a negative 2, and capital C would be a 7. That is what we call a linear equation. Right? Now, not all linear equations are going to look exactly like this or have this exact format, ax plus by equals c. Sometimes you'll see a linear equation that maybe looks like this. Now that one should look kind of familiar to you. But this is also a linear equation. You're saying, well, that doesn't look like this. The equal says it in the wrong place. Well, you can make it look like the ax plus by equals c by simply subtracting 4x. Now we're going to see you don't actually want to do that, but you can, write it that way to show that it does have that ax plus by equals c format. And now you can see, well, yeah, a is negative 4, b is 1, not 0, that is a 1 in front of that y, and c is negative 1. Right? And these can take on many different shapes. The bottom line is you're looking for basically your variables x and y to be to the first power. Nothing funny like x multiplied to y or absolute values, if you remember those symbols. If you see a variable in the absolute value, that kind of ruins it as a linear equation. You see square roots of variables. You see a variable in the denominator of a fraction. Those are all disqualifiers for linear equations. It has to be oh so basic. X to the first, y to the first. If it has those two components, most likely it is a linear equation. So many times you'll see a linear equation written this way, or they might say, okay, we got y minus 7 equals 2/3 times the quantity x plus 5. You look at that and say, is that a linear equation? The answer is yeah, it has to be. How do I know? Well, it's plain old y to the first. That's plain old x to the first. Yeah, you got some fractions and quantities running around. They're not on the same side together. So what? I'm not saying it's exactly in this form, but I am saying it's a linear equation. Now, what does that mean when you say something's a linear equation? Well, let's take an example. If I said, hey, think of two numbers that add up to be 10. So if I said, think of two numbers that add up to be 10. Let's just get a list here. You've got lots of possibilities here. Two numbers that add up to be 10. Well, you could go with 5 and 5. That works. First number's 5, second number's 5. Or you could say 3 and 7. And why not say 7 and 3? Just reverse it. You could say 1 and 9. You could say negative 2 and 12. Or 12 and negative 2. And the list is endless. I mean, you can get real crazy here. Two numbers that add up to be 10. You could go on all day. As long as someone picks the first number, I can easily figure out the second number. Well, what if we think of these as ordered pairs? Say, okay, so what does that do? Well, what if we were to plot these ordered pairs? Are they just going to be a bunch of random dots all over the Cartesian coordinate system with no rhyme or reason to them? The answer is clearly no. There's going to be a system to this. Now, without turning on the overhead here, just real quickly show this. If I plot 5, 5, that would be a point right there. 3, 7. Okay. 3 and 7. And we got 7 and 3. 7, 3. 1, 9. Pick some smaller numbers. So, too late now. 1, 9. We could go with 9, 1, I guess. 7, 8, 9, 1, negative 2, 12. Now I'm really wishing I didn't do that. Negative 2, there's 9. That's not a good spot. 10, 11, 12, etc. And if you plotted every single number where the two numbers add up to be 10, what you're going to get is you're going to get all your points, and I missed right there. You're going to get all your points lining up. Literally, they form a line. And the reason they form a line is because this represents a linear equation. Give me two numbers that add up to be 10. What's your first number? I don't know. Let's say x. What's your second number? Don't say x again unless you're talking about this exact one where they're the same numbers. His first one's x, the second one's y. You add them up, you get 10. Well, take a look. That's a linear equation. The capital A is 1, the capital B is 1, the capital C is 10. Or we could just say x and y are both to the first power, nice and friendly. It's a linear equation. This forms a line. Hence the term linear. Root word, line. It's a line. Every time you graph a linear equation, you are graphing a line guaranteed. So no matter how complicated you may make it, even something like this, it's still some sort of line, as demonstrated by this. Now, as far as the forms for a line, this is known as standard form, and it's just not very useful to us. You'll see lines many times written this way, 3x minus 2y equals 7. You might like seeing it like that, but it's not very helpful as far as telling us certain things about the line. We're more interested in what's called slope-intercept form. So that one's a big one. Something I think you are familiar with. All right, so it's called a slope-intercept form. It's a special way we write our linear equations. Like I said, this is called standard form, where you have your x, your y on the same side equals a number. This right here, this y equals 4x minus 1, that's an example of slope-intercept form. This down there, that's another type of form that we do need to talk about. But slope-intercept form will say when a linear equation is solved for the y variable. What would that look like? Well, there is one time that you can't actually solve for the y. If you make your b here 0, that's a problem. That would not be slope-intercept form, and we could never write in slope-intercept form. But every other time, we can solve the equation for the y variable. In other words, isolate the y variable, and you are putting it in what's called slope-intercept form. So what you would get is an equation that looks like y equals every single time. You're solving for the y variable, and there would be some number that would get multiplied to x, and there'd be some number that would be added or subtracted on. And this should look very familiar, y equals mx plus b, because these numbers, or these letters m and b, represent numbers. They will represent actual numbers that mean something to us as far as our line is concerned. So when a linear equation is solved for the y variable, you get this. Let's just put, you have what's called slope-intercept form. Intercept form, and let's be specific where this m right here is the slope of the line. I'm really having troubles here today. Is the slope of the line, and b is the y-intercept. So when we solve for the y variable, we necessarily get what's called slope-intercept form. Right? Again, the m is known as the slope, and the b right here is called the y-intercept, or is known as the y-intercept. Writing an equation in this format, this slope-intercept form, is so helpful for not only graphing the line itself, but for finding special parts of the line, particularly the slope and the y-intercept. Right? In the next video, we'll kind of go over some of these things. We'll go over what this slope and this y-intercept do, and exactly how it leads us to graphing these lines, these linear equations.